But very quickly, let's talk about the reason we do what we do, where the process comes from. Then we'll try some problems out. We're trying to work our way back up to that last problem we had started to do, where the rotation axis wasn't one of the x or y axes. So if I have some region, here's my region. I'm going to rotate it around, let's say in this case, let's say around the x-axis. Stay with it. So it's going to create this three-dimensional figure, right? This maybe looks sort of like a, if I had the empty middle, it might look like a flower pot or something, right? I mean, it's like that, and it's rotated, it's horrible, but rotate. So this comes out, it's 3D. So again, in the book, if you have OSI, it's really cool because you can access the 3D stuff that I use in class. So the whole idea here is every single position on the x-axis has associated with it a disk. So if I rotate every point, if I take that point and I rotate it around 360 degrees, that's going to define its own circle, which we officially call disks. Right? If I find the area of each of those disks multiplied by how many disks there are, that is going to end up being the volume. So let that just make sense. In fact, I think last time we did talk about how do I get the area of that, pretending like it's a straight up. That's what a can looks like after you've had a few.
If you squash it.
Everything's Picasso or something. How would you do this? It would be the area of this bottom and then times how long it's repeated for. That's exactly what we're doing, except I don't have, what this represents. A perfectly repeated shape. It's the radius of the circle is changing as governed by this function. All right. So every time I move a little bit on the x-axis, the corresponding circle's radius changes according to whatever the hell this function is. So what I do then is I have, what's the area of any circle then? Of any of these disks? What's the area? And what's the R? Yeah, so the area of any of these is going to be pi times f of x. We just write it like that to be really, really clear. And so if I want the volume to integrate the area over the entire range of x's, so I just end up with integral pi f of x squared dm. Now why is this radius really easy? Because the radius starts where? On the x-axis, which is a y of 0, right? So if my radius, if my rotation axis is not one of the main axes, I've got to be careful about what my radius really is. So that's where we're working towards. Yes, sir.
Is the second f a large f, or is like?
Oh, I'm sorry. It's just me being.
So it's not big ass f.
No, it's not big ass f.
Okay.
I like it.
So it hasn't been integrated yet.
No, it has not been integrated yet. I like it. Is everybody cool with that? I mean, it's almost, if you let it be. I mean, can you guys see that? If I rotate anything you give me, if I rotate every point on it, every point's going to make its own disk. Each one of those disks is going to have this area.
And even if it's some crazy shape.
You're doing a seance? What?
Even if it's a crazy shape.
Exactly. It's the beautiful thing about it. This shape could be as insane as it wants to be. And every single little x doesn't care. It makes its own disk. And then the next one makes its own disk. And the next one makes its own disk. So we're slicing it. You can imagine this piece of ham that you got. And it's all, you slice it and you slice it and you slice it. And you keep making these. Well, it's not perfect, but anyway, you get the idea.
It wasn't like a function and it went back over itself. Would this process work?
You can actually do a process like this, but then you'd have to use parametric. Well, you guys remember parametric, where the real variable is t, it's the background variable. The t-axis doesn't show. Oh shit. Well, anyway, yes. The short answer is sure. Not here. Not now. Yeah. All right. So let's use a real function here and do a real problem. One that's basically just like this. So let's use what you got, Jeff? I don't know, man. I think I did one like this last time. So I just write it like that, so it's really easy for me to graph. Well, that's going to be kind of gross. Let's make this 1. Simple. You guys see why I did that? So I want to use the region defined by the function and the x-axis in the first quadrant, and rotate it around the x-axis. Okay. So the book has to give you all this information to tell you exactly what the region is defined to be, where you're rotating around. So to graph this real quick, can somebody help me out? Yes, upside down parabola. It's been lifted up by 1. So at 3, this is a value of 1. And 1 away from that, it's going to have a value of 0. So there's my region, right? Just a little tiny thing. I want to make something sort of manageable. So when I rotate this around, I'm going to get this weird little ball shape, right? It's not going to be a perfect circle because this is parabolic, which is not the same curvature as a circle. Some weird little fat, stubby football thing. Right? Squeaky toy for a dog or something. All right. So let it go, Jeff. It doesn't matter what you use it for. All right. So I'm going, obviously, I'm going to rotate around the x-axis. What are my limits going to be? 2 to 4. I love it. See, all I have is a 2D picture. I know that it's going to end up representing a 3D object, but that does not make the actual integral look 3D or something. No, it's going to lose the idea of it pretty quickly. But I'm going to rotate this bad boy around, so it's going to look like that. Right? And if I would have been really, oh well, let it go, Jim. Sorry. Okay, so I'm rotating around the x-axis. The nice thing is, I don't know if you guys remember this, the disk method, it's integral d axis you're rotating around or parallel to. So if I'm rotating around the x-axis or some line parallel to the x-axis, it's going to be dx. Why is that important? Because it tells me how my function has to be written. Is my function in terms of x? Yes. So if I wanted to use dy for some reason, if I had to, I would have to solve this for x somehow. Thank God we don't have to. So to make this look a little better, when you multiply this out, what do you get?
1
Yeah, well, yeah. So you get negative x squared minus 6x, so plus 6x,
6x plus 9.
minus 9 plus 1, so minus 8. And just to double check, when you plug a 3 in, you get negative 9 plus 18 is 9 minus 8 is 1. Yay, all right. Just make sure we multiply correctly. So that's the function I'm using. So what does that function represent here for my disks? So some arbitrary point x. What does that function represent? The radius. I love it. It represents the radius. Kick ass. So all you have to do is draw the 2D shape, the region that you're dealing with. You don't have to draw any 3D, thank the gods, unless you can, and I will be impressed. I will. Look, for me, this is beautiful for me, actually, and it's more than I really need to be able to do the problem. I already know I'm going along dx, so what's my limits from to? 2 to 4. And it's going to be pi times the radius squared, and we know the radius is just going to be this. It's really that minus 0, because I'm on the 0 line, right? I'm rotating around the 0 line. So if I was rotating around the y equals negative 1, it would have been this minus negative 1. That's how far it was away from this. But the radius is how far the edge is from the center. But my center is the x-axis. Easy. So then the only bad thing about this is I got to square this bad boy, right? That's really the only bad thing about disk method is whatever your function is, you're going to have to square it. So it's nice if it's a radical. If it's a square root, the squaring of the inside is going to kill that square root. But if it's some polynomial, oh shit, you got to FOIL that polynomial out. Yes, no, maybe so? All right, so then this would become... Let me write like this real quick just to make it look easier. I can just kill all the negatives inside. Hopefully you guys are cool with that. So then I get x to the fourth minus, let's see, plus 8x squared minus 6x squared. Are you going to really try to do all this in your head, Joe? Yeah, I was going to. So x to the fourth minus 6x squared, x cubed, sorry. Plus 8x squared minus another 6x cubed plus 36x squared minus 48x, and then 8 goes through. Are you guys cool with it? Come on. The real heart of what we have to do here is this. Once you get this set up, you should be golden. You should be ready to go. Even integrating this, it's just a polynomial. I mean, it's a little gross to FOIL it out, but it's just a polynomial. You can't ask for a better thing to integrate, except for e to the x. And then you would plug in the 4 and plug in the 2, and you're done. It's almost too good to believe. Yes?
Wait, why did you multiply the 2 polynomials together?
Because it was radius squared. So I got a square, yeah. Cool. All right, so what I want to do... All right. Let's try... Let me see, I want to figure out which order I want to introduce the weirdness. Let's do this. Let's use a function that's not too weird. Let's do this in stages. So let's talk about one. Well, let's see if you pick up on what's going to change here. Really good thing I always do is draw the region. Do that first. And then let's see if you figure out what the second step is. Oh, let me give you a top here. X equals 0. Let's say y equals... What you got, Jeff? 4 is fine. So I had it open top. It would go to infinity, and then that would be kind of weird. So y equals 4x, so it's 0, 0. And I want to go between... What's x equals 0? What does that mean?
Afterwards.
That is the what?
X.
No, it's not.
What?
The x-axis, x is everything.
The y-axis.
Y-axis, I like it. So y equals 0 is the x-axis. Cool. So I want the region between this line, the y-axis, and y equals 4. Well, at x equal to 1, what's the value of this? 4. So I've just defined the region I'm talking about is this little triangular region there. And I'm rotating around the y-axis. Can somebody help me? How does that immediately help me do the most important next step?
Solve for what?
Yeah, and y. So what's the really good next step is to write what your integral means. Since I'm going around the y-axis, if I want to use this method, I got to use dy. Kick ass. I write that down immediately so it keeps me focused. I need everything that goes in here to be in terms of y. Do I have that right now? No. So like Troy said, how do you solve this for y? I mean, for x? Good. Y over 4. So that's this function here. Because now, how am I going to locate my disks once I rotate this bad boy around? Where are my disks going to sit? How do I want to say that? Like here, the disks sat on the x-axis. Do you see that? They're going to sit on the y-axis. That's why this is going to be dy. That's the reason behind it. But now it becomes really quick. If I'm using disk method, rotate around anything parallel to the y-axis, dy. Vice versa for the x. That's awesome. So the other method we're going to talk about is just going to be the reverse of that. So now any disks I find, their radius is going to go out to this. What is this function now? Better? Y over 4. I like it. Cool. So that is my question. Radius. That's the radius of any circle in there that I can draw. I like it. So do you see the steps I've taken? I don't know what this is before I've done it, right? I just made this up out of nowhere. So I've got to draw the region I'm talking about, rotate so I can find a little circle there if you want to, but you really don't even need to draw the circle. All you need to realize is it's from the rotation axis out to the curve. So how long is that? It's this long. So in here I'm going to put, what's my limits going to be for dy? 0. If it was dx, it would be 0 to 1. Kick ass. 0 to 4. And what do I put on the inside?
Y over 4 squared.
Yeah, pi r squared. Because I'm just adding up a bunch of circle areas. That's all I'm doing. If I add a bunch of circular areas, I end up with the whole volume. It's almost too nice to believe. And now this is a nice integral. It's going to do pi over 16. And what's the integral of y squared?
Y cubed over 3.
Yeah. From
0 to
0 to 4. So we're cool with that. Took the 16 out of the way. Y squared becomes 1/3 y cubed. Antiderivative.
60.
So 0 will be 0. So all I got to worry about is pulling a 4 in there. 4 cubed is
64.
divided by 16.
4.
4. So I get 4/3 pi. I'll just stop there for a second. For most of our functions we're going to see, once I get this integral set up, the rest of it should be gravy. Should be gravy. The biggest thing people forget is to do that correctly or to do that at all. Alright, how can I get a feel for if this is right or not? What shape did we actually just create?
A cone.
And what's the radius at the top? 1. And how tall is it? 4. So the volume of a cone is 1/3 pi r cubed. Gather cubed, squared h. Oh, where the hell I came from?
Yeah.
So it's 1/3 pi, radius is 1, and the height is 4. I get 4 frickin' thirds pi. Of course I do.
Holy shit.
Holy shit. So this is good. So hopefully you're past the point. Nobody's going to say, well, why do we do that shit? Why can't I just do that? Because you can't always do that. It's power calculus. It can take a shape that I have no idea what the hell it does, and it can just attack it and figure out the volume. I don't have a geometric formula if this is all curvy and shit. But calculus doesn't care. Alright, alright. I just like to do a shape that we can do 2 ways. So you kind of buy into this a little bit more.
But as you said, only easy shapes, right?
Yeah, exactly. I mean, this one, there's no way to do it geometric. I showed you last time how you can kind of approximate sometimes. But even then, you got to be careful. So let's do one where the axis is not the y or x. And then we'll do this, the back of that handout I gave out last time. Off-axis rotation. So say we have it. I'm sorry. Sure. I like it. So the one more thing I got to tell you. Say x equals 5. Sure. All right. So the region is defined by this, the area between those two, and it's rotated around x equals 1. So they have to tell you what your 2D area looks like, and then they got to tell you what you're going to rotate that thing around. All right. So of course they gave us something nice. It's from 1, basically that's my rotation axis, is around x equal 1, up to 5. And I said 5 because what happens at 5? Being all nice, yeah. You get 2. So here's my region basically, is like the square root. I like it. And we're going to rotate this thing around the x-axis. If I was going to rotate it around the y-axis, not the x, what am I talking about? I'm going to rotate it around this line here. If I was going to rotate it around something here, it would make a nice bowl shape. I'm rotating around this thing, so it's going to make this weird top of a freaking glass for wine or whatever. Right? Cocktail glass, what are you going to call it?
Martini glass?
Martini glass, thank you. I knew it was some word like that. I drink a lot, obviously. right, let me stop there for a second. You guys semi with me. So you can actually do all the work based on what I've drawn already. What's the radius going to be? Let me just draw a straight line. So here's, let me find. So I'm rotating around something parallel to what? Yeah, what is this parallel to? The y-axis. So I need integral what? So I need my function to be in terms of
Y.
Y. I like it. And the nice thing is, I mean, it's really easy to solve this for x. Right now it's in terms of x. I need it in terms of y. So what will this become?
Y squared plus 1.
Yeah, y squared plus 1. But I really want you to see the steps I go through. Draw the region. Then write your integral, leave room, d whatever. I'm rotating around something parallel to the y-axis, so it's got to be dy. I like it. Now what's my radius going to be? So pick some arbitrary y piece. This radius is right there. Here's the beautiful thing about what I just drew. It's always the bigger thing minus the smaller thing. So where do I end? The function. And what is this function?
Y squared.
Good. And that's the bigger thing. Minus the smaller thing. And what's the smaller thing? 1. I love it. So this is what x is on this side. This is what x is on this side. So what's the radius? The difference in those two things. It's always the bigger minus the smaller. Even when it's a negative freaking thing, who gives a shit? It'll be bigger minus smaller. Minus a negative is plus. You don't have to worry about that ahead of time. You just subtract the two. Bigger minus smaller. Always. For the radius.
So it's y squared.
So my radius is going to be, yeah, y squared plus 1 minus 1. So y squared. And just to check it. Let's see. At 0, what's the radius? How far away from it am I? At 0, what's the radius? 0. I love it. And at y equals 2, what's the radius going to be?
4.
4. And does it make sense? How far apart are these?
4.
You can always check your radius. Make sure it makes sense. Take some extreme values. Make sure they make sense. Okay, maybe. And the thing to remember about any process you learn, you have to trust the setup of the process. Adding a bunch of circles to get the whole volume, that by itself should be awesome. That should be, okay, that makes sense. So every time I set up this integral, that's what I'm setting up. It's going to almost immediately not look like that anymore once I start working with it. So I just got to let that go. I got to trust that the integral will give me what I need. So I'm going to add up a bunch of circles. What are they going to look like? Pi.
Y squared.
Y squared. Squared. See, that's the thing. Your brain says it's already squared. No, that's r. R's got to be freaking squared. Whatever you find r to be, you got to square it when you put it in there. So you make your circles.
1 pi.
Yeah, so y4, the integral of that is... oh, I'm sorry, from where to where? Careful now. Yeah, what's the limits on this thing?
0 to 2.
Beautiful, 0 to 2. How do I know it's not 1 to 5?
Because
It's dy. See, that's why, that's the second thing I do, is write down dy or dx. Because I can continuously look at that and keep me straight. Everything's got to be in terms of y. So what does the y do? 0 to 2.
So it's y to the
Yeah, y to the 4th, so then you integrate that, you get...
y5 and y5.
Yeah.
So it's going to be 32 over 5 pi.
Yeah, 32 pi. When you throw a 2 in, you get 32. 32 pi over 5. I like it. Is that a shape I can check with geometry? Hell no. Not easy. I can estimate it by pretending it's a cone and make that straight. But then I know that my estimate's going to come out bigger than what I actually got. Does that make sense?
Yes.
Yes. So there's always kind of a way to estimate it, but it's not always immediately obvious how to do it. Hey, you're back. All right, so let's do this. I got 5 minutes to see how far I can get on that handout. these now, right? Alright. So yours will look slightly different than mine. We'll see in a minute. One little crucial piece of information got cut off when I reformatted it. So yours does not have this. That's kind of important for me to tell you. So right up here on that first little problem, you got this whole line here, right? But then I say about the x-axis. Kind of important to know where the hell you're rotating this thing around. And if you're curious, if you get further along in math, you can do diagonal line. You can rotate around y equals x, for example. You can do this weird side diagonal rotation. It's a little bit more difficult. So the very first thing you do, so here's the problem. I would say find the volume obtained when you rotate this region around the x-axis. So of course, what's the very first thing I do? Draw the region. I love it. So y equals x squared. X equals 2. Where's x equals 2?
2.
Oh, yes. It's right there, but it's like this whole thing, right? So where do these things meet? That's going to be one edge of the region, one corner of the region. Where do they meet, of course?
At 4.
At 4. So x equals 2 is like this. Y equals x squared is like this. Let me stop there for a second. So you want to find out, and y equals 0, of course, is the x axis. Cool. That's why I'm just starting here. I like it. So that's the region we're talking about. And I'm going to rotate it around the x-axis. So the next step is what? You don't have to.
Right, dx?
Yes, so it's integral dx. That's what's going to keep me focused. So I mean, everything I plug in there has got to be in terms of x. All the limits I use have to be what x does. That's why this is such an important step. It tells you what variable to keep in mind as you're setting this thing up. So is my function in terms of x? What's my radius? Let's be sure we know what the hell we're talking about. It's about the x-axis. So how far do I have to go when I go any x I want? How far is that?
Function.
The function. I love it. So it's not off-axis. So it's exactly equal to the function because it's minus 0. X-axis is where y is 0. So the radius is x squared. So it'll be pi times
X squared squared.
x squared squared. I love it. From what to what? Good. You're. It's all about what x does. That's why this is such an important step. I know I'm saying things again, but I have to. And now that's very much like what we just did. In fact, it's the same exact thing, just about, right? If you realize something is anyway, it is the same thing. So you get pi 1/5 x to the 5th from 0 to 2. So again, you get your 32 pi over 5. I like it. So the important thing is setting up the integral. The rest of it should not be the hard part. The hard part should be getting here. Let's try to squeeze in one more. Let's see what happens. You guys are fading. Sorry. So I've got the same exact region. Right? So it's the same exact region. So now I'm rotating around y equals negative 2. So I'm going around y equals negative 2. This thing there. So I'm going to try to do this without. When I was trying to draw the image, the mirror image, and trying to show you the discs, I'm trying to show you the idea behind what we're doing. I don't need to do any of that when I go to work this out. What is the radius going to be? Start where?
Function plus 2.
Yeah, so if I go from the rotation axis all the way until I hit the edge, that's going to be the function minus negative 2. It's going to be the function plus 2. I love it. You guys see that? It's 2 more than it used to be on the first problem. So my radius is going to be exactly what now?
X squared plus 2.
I skipped this step because we know it's already dx. We already did that. And now it's the same exact problem. My radius is a little worse, right? is still going to go from where to where?
0 to 2.
0 to 2. My x is still doing the same thing. So now my radius is x squared plus 2. Put a little pi in there. So there's my pi r squared. Make sure you find each of those when you write that down before you start doing anything, any integration. And now you would FOIL out and plug in your values. That's funny to do anything. We'll do the next two next time.